Okay, let's switch some gears and look at backend. We all need backend. This is Madhur from NVIDIA. I'm going to talk about my work, our work on GlobalISel, from fallbacks to performance towards better GlobalISel performance. This was done in collaboration with Dhruv and Tiani. We'll quickly go over GlobalISel for contributions, results, and the next steps. So for those who are not very aware of GlobalISel, it's basically yet another instruction selector. In the code base, it's been there for more than 5 years. It is now default at 0 at AArch64. But for other cases, like for other optimization levels, it just falls back to SelectionDAG, right? But when you look at the GlobalISel as an infrastructure, it doesn't create the new IR called DAG. And it just goes through the generic machine instructions and lowers that to the machine instructions and refines that through the multiple phases. But when we compiled with the different benchmarks, we found that a lot of them, or almost all of them, just falls back to the SelectionDAG. So in the longer term, we do want to enable it at 03 for the AArch64 backend. But our approach is empirical. We do want to go with the benchmark by benchmark and see what is happening. But do we have a plan at this point? No, we don't have a plan. Do we know what the check boxes we want to tick? That's also not known. But where do we start? So we want to start with something small and simple. And fortunately, there is a small benchmark called TSVC, which stands for Test Suite for the Vectorizing Compilers. It was written with the purpose of tuning vectorizers, but it is very small enough that gets the ball rolling, and it helps us in analyzing. It has a 152 small computation kernels. Each starts with a alphabet S and then a number. And for the scope of this talk, I'm going to focus on GlobalISel flag and the MCPU equal to grace. So when we compiled back in February 2024, we found that there is just this one kernel which falls back. Everything is nice, but this kernel particularly falls back to SelectionDAG. So if you look at this small kernel, it's not pretty big, but through the IR, it generates fmuls, but through the vectorizer, it gets to the interleave and de-interleave intrinsics. We looked at the SDAG implementation. We found that they're getting lowered with the naive shuffle vectors, and we just imitated that in our GlobalISel path, and the patch details are there. And this was a first milestone of our work. But what about performance, right? Because after all, we have to tackle GlobalISel against the SelectionDAG. So if you look at this graph, upper half shows GlobalISel were faster, lower shows GlobalISel slower, and there are 3 kernels which are basically very slow performant when compared to SelectionDAG. Let's zoom in the first kernel. In the first kernel, if you see that it's again a pretty small kernel, but if you see FCMPs and selects, and later you see freeze instruction. So through the pass pipeline, through the phases, it was basically getting scalarized, which is not good because eventually you have the unnecessary instructions there. And we fixed the exact same problem. We avoided this scalarization by adding the rules in the rule set, and eventually it just helped to fix the gap. This was a patch which contributed majorly, but we have other patches also. We provided the details. But after you commit this patch, we see that this particular kernel, which was more than 50% behind SelectionDAG, it just get fixed. But you still have those 2 other guys, where 3110 and 3111, which are basically the same kernel, but that was sort of blocking the performance of the entire test suite. If you look at that kernel further, zooming in, and here it's a very simple kernel which takes a maximum of a 2D array. Very naively it computes it. There is no extra business going on here. But if you look through the GlobalISel path, it has load, FCMP, and max, and which was sort of expected. But if you look further through the multiple phases, you see that there is a load instruction in the for loop, and beyond that there are multiple copies instruction. But if you note very carefully, the first load instruction is happening in some general purpose register. And in the copy, you see that the general purpose registers are getting copied to FPR, floating point register bank, and then again back from FPR to GPR, right? Which doesn't make sense, because if you have the users in the FPR bank Why are you loading in the GPR bank? That was the first question we asked. And when we digged up more in that, we see that the reg bank select pass, which basically is responsible for doing all this analysis and assigning the register bank, was not very matured enough. And this is where GlobalISel helps us, because why we should invest in GlobalISel is it allows us to look beyond basic blocks. SelectionDAG is limited only to the basic block, but GlobalISel goes beyond the basic block and can trigger the selection or can trigger the optimization, which are not possible with the SelectionDAG. And that this particular kernel shows the capability. So we just exploited this. We just augmented the fee node mechanism, or the mechanism which looks beyond the fee nodes, and we found that, and we augmented that. If you are loading in a floating point register or a general purpose register, but your uses are in a certain different register, then why don't you take that into account and use the same register bank for your all the load and the store business? And this was the major implementation, and this was a major contribution for this particular kernel. Now, we are talking about multiple patches here for the fixing of a particular kernel, for the entire benchmark. But if you look at the before and the after graph, you basically close all the gap as a combination of these sort of 11 or 12 patches. And the entire test suite now is very close to SelectionDAG, the performance-wise. But a curious reader will note that the y-axis on the after graph is sort of shrunk. Its maximum is minus 20%, and here it was 75% because there were performance degradation. But the minus 20% is coming only because of the noise, because if you remember that these are pretty small computation kernels and there is a lot of noise. Even if you run it for 5 times, take the geometric mean or take the minimum or whatever statistical techniques you do, there is still some sort of a noise in that. And getting rid of that noise is not pretty worth, right? And because it may not lead to the new opportunities. So at this point, we sort of declare that we are in a ballpark distance with the SelectionDAG, barring the noise and other things. Finally, in the final section, I just want to say that we took the small benchmark, TSVC, and we showed that how you can augment the performance and how you can fix the fallbacks. And you could go also beyond the capabilities of the SelectionDAG. You could propagate the information beyond the basic block, which triggers the new optimization opportunities. And this benchmark just gave us the right platform to demonstrate that the GlobalISel has enough capabilities to do all sorts of optimization. And fortunately, this was done without any loss of compile time, because we remember that GlobalISel is meant to improve the compile time. The promise is on the paper is that we want to improve the compile time. So, of course, if you are doing any optimization, then you don't want to lose the compile time promise. So, when we, after the patches, when we collected all the compile time numbers, we do not have any regressions. That's a good thing. But we also get the performance back, right? So that's the one of the important conclusion. But did the story end here? Definitely not, unfortunately not, because when you look at other benchmarks, there are a lot of fallbacks, right? But interesting thing is in the spec 2017 benchmark, which is a very important for the CPU guys, 4 out of 9 benchmarks are compiling without falling back to SelectionDAG, which means that we are partially functional complete, or at least for the spec 2017. But for the other benchmarks, like RajaPerf, LLVM Test Suite, and all that, you need point fixes. And the major theme now we are observing here is that the inline ASM is not very supported. So we just need to look at the DAG and see how we can get through it. And we have a small CI running internally, which basically takes the builds the LLVM at the top of the trunk and collect these fallbacks at using some scripts and all that. So these numbers are just like from the last week. So these are very close to the reality, not like 1 month ago or something. So you do have a lot of fallbacks there, and we are actively working on closing that fallback and eventually going to the dream and saying that, oh, yes, AArch64 has a O3 enabled by default, so it's not going to be a one-man or one-team effort. Patches welcome and come join us. Thank you for attending, and special thanks to all the patch reviewers.
Thank you, Madhur.